stack on B2B and B2I communication. The overview of the presentation is this. Related to DSRC component, then I will explain the test bed and the results, then I will conclude. Everybody is familiar with the traffic conditions that is getting worsened day by day. So for that, there has been a lot of research has been going on in the world, worldwide. And according to WHO, on this one survey, there are 0.1 million lives that are lost in India due to traffic accidents. And it is also believed that most of the accidents can be avoided if the information to the driver is provided just seconds before the event. So there comes DSRC. DSRC stands for Dedicated Short Range Communication. What is DSRC? DSRC is a suite of standards to enable vehicular safety communication, and it mainly comprises of 802.11p, that is wave, then 1602.1, 1602.2, 3 and 4. Plus, it also uses one message set dictionary, that is SAE J2735. SAE is the Society of Automobile Engineers. Basically, this research has been going on mostly in USA, and we are working on their FCC spectrum allocation. So it basically ranges from 5.850 gigahertz to 5.925, and it has been divided into two kinds of channels. One is the control channel, and other 6 are the service channels. So they are basically 10 megahertz bands. TCH is basically used for control information and also for sending basic safety messages. And according to the IEEE specification, every device has to switch to CCH periodically so as to get the control information. And here we see it as a wave stack, as it has been. It is comprised of many protocols. You can see that the physical layer is defined by 802.11p. Then the MAC layer is defined by 802.160.4, then the LLC. Then there is dual operation. We can also use IP and UDP. Plus there is one new protocol that is defined by 1609.3, which is WSMP, Wave Short Message Protocol. Then there is a management plane, which takes care of all the management activities in the protocol. Then the security services are defined by 1609.2. The main objective of this paper is to present the results of the tests conducted in real-time environment over the wave-enabled hardware. This hardware we have bought off the shelf, and the tests conducted mainly evaluate the performance, while mainly wireless performance parameters. The parameters that we have calculated include delay. Delay is basically the return time delay between the packets. The significance of calculating delay is to measure the latency between the packets. As this is a vehicular communication, the latency of the communication has to be very low. Then we have calculated jitter. Jitter is the mean deviation of the difference between the packet delays. And the significance of jitter is it basically measure the stability, whether there is a variation, a lot of variation in the delay is there or not. Packet loss is, everybody knows, packet loss is the percentage of packets received to the packet sent. Then we are conducting these tests under various channel load in the current channel and also in the cross channel. The related work, most of the work that has been done before has been done on simulators, and the two most important studies that are of most significance are by AGFRE Al-Khayat document. They measure the performance evaluation of IEEE 802.11p for vehicular communication networks in NS2 simulators. Then there is work by K. Carlson, C. Bergener, they do the field measurements of IEEE 802.11p communication in non-line of sight environments. The first paper, it basically talks about the tests conducted in NS2 simulators, which is widely believed that such testing models may not be very accurate because they use very general algorithms for modeling the environment. The second paper gives results on tests conducted in real time. They calculate packet error rate and the RTD. They have done this research mainly for non-line of sight and line of sight parameters majorly. I would like to introduce these the basic components of DSRC. The DSRC basically comprises RSU, OBU, and one server. OBU is the onboard unit and RSU is the roadside unit. OBUs are kept upon the vehicles and roadside units are kept on the poles on the roadside. The RSU, they form a they form a backhaul network and which is in turn connected to a server, so that the information from server can be transmitted to the RSU, which in turn can communicate with the OBU. This is a test bed. We basically took two OBUs and one RSU. We put one RSU on the pole at 6 meters height. Then one OBU we put on the car, and other OBU was used to generate the load in the channel. This is the pictures of this. There is OBU on the car, and this is the RSU on the pole. The road stretch that we conducted our test had a huge dip in the middle, which was its depth was more than 2 meters, and this is the Google view of the road. Among the results, we conducted first test for this is the test for without load. There have been for channel 172, we can see that between 200 to 500 meters there is a heavy loss, and correspondingly there is loss for 178 also. 178 works on a higher power level, so there is a less loss in 178. Similarly, we can see that for jitter and average delay there is almost there is no variation with distance. We can see these are the graphs for delay characteristics. The first graph is for load on the same channel, and the second is for load on adjacent channel. You can see that the RTD did not vary very much with the distance, and also it did not vary because of the load on the same channel, but there was a large loss when the load was put on the adjacent channel. For 300 meters, we did not get any packets because of the dip that created a non-line of sight. Then there is the measurement for jitter. The jitter values were also found to be increased when the load on the adjacent channel was increased. That created cross-channel interference. So with distance, we did not find any effect on jitter. For 300 meters, we did not get any packets. That is the same reason. These are the graphs for packet loss. For packet loss, we can see that as the dip started, there is a lot of packet loss, and the dip was between 200 to 500. And similarly, we can see that the packet loss, which was between 80, which was about 82 to 83% maximum in load on same channel, when the adjacent channel load was applied, the packet loss increased up to 90%. So the conclusions that we made out of that there was a sudden rise in the packet loss after 200 meters. That was due to the dip in the road, which created non-line of sight. Next, the average delay and jitter. There was no considerable change recorded in the average delay and jitter. They were almost non-varying, and the average delay that we recorded was between 2 to 3 milliseconds, and average inter-arrival jitter that we calculated was between 0.4 to 1.3 milliseconds. The effect of adjacent channel is what the main parameter that we could say it had its more effect. it had effect on all packet loss, return and delay significant. The stricter channel mask need to be applied for controlling the power in the bands, and or we can control the power in the adjacent channel. We can keep it low so that the loss created by this adjacent channel interference can be reduced. And level installation of the RSU can also be done in such areas where the land is uneven. We can put the RSU at places where the dip starts, such that it is visible to all of the vehicles inside the dip. Currently, we are focusing on to V2I application development, and we are creating applications which give audio visual warnings and speed limit. And in future, we are going to design development of cost-effective DSRC enabled hardware with wave stack.
So you mean to say your work is not cost effective?
No, actually, this test we have done. We have got the hardware from off the shelf. So we have conducted the test, and in future when we will make our own hardware, we will be making them less.
Actually, packet loss, so that is a known fact, right? When you are out of range, you don't receive the packets. You don't have to conduct such an experiment and
No, basically what new thing we have done, we have calculated, we have evaluated the effect of adjacent channel.
Adjacent channel interference.
Those things are done by other people also,
Yeah.
and the results are almost same as them. But the evaluation adjacent channel has not been done very much.
So your focus is on adjacent channel interference, and you hope to reduce it.
We think currently they are using class C channel mask, and also we think that if we increase it to D, then these cross channel interference may be reduced, and also there may be other techniques are also there. As I told, we can, suppose there is a 178 channel is there, it is the most important channel. So to reduce the effect of cross channel on 178, we can the power in the 176 channel can be kept low.